Santi, and everyone here will guess how to pronounce this.
Not this one much. Okay, we'll do my best. Okay, cool. We can get started. Thank you for that. All right. Natalí Matubaro Santi is a physicist and machine learning researcher working at the intersection of cosmology, astrophysics, and artificial intelligence. She earned her PhD in physics from the University of Sao Paulo in 2024, and during her doctoral studies worked as a pre-doctoral and guest researcher at the Flatiron Institute, Science Foundation, later returning as a visiting scholar in 2024. She also holds a master's degree in physics from the Federal University of San Carlos and a bachelor's degree in physics from USP in 2015. Oh, and I forgot to say thanks for coming to today's lecture. So yes, let's give a warm round of applause for our speakers.
So hi everyone, thanks for having me here today. And you pronounced it like everything perfectly. Yeah, well, my name is pretty like hard here, so well, that's okay. So I imagine that you are here today to think a bit about how to unraveling the cosmos using machine learning. And the main idea of this presentation, or at least the way that I would like to start, is like, okay, can we try to use machine learning to understand the universe? Well, we actually know that there are lots of things that we kind of like don't understand it, like in your universe. But right now, machine learning, apart from being like something really hot, a really hot topic, is something that we can use to do some cosmology. And one of like the main motivations for this is because nowadays we have lots of observational data and lots of simulation data. So because we have like this huge amount of data, we actually have traditional ways and techniques to extract information from this data, although machine learning could help us to extract some different kind of information, or even some like being used as another machinery to extract the same kind of information from the traditional methods, maybe in a better way. Let's see. And then one of like the main motivations is because we can use machine learning to actually like extract really nice informations and intricate informations from images. You can use them to extract information directly from the fields. And these networks are very, very good to actually like give like some kind of answers for us that, for instance, direct methods don't do, right? But even though they could be just like an alternative method. So how do we describe the universe? I believe that this is one of like the main things that we think about it when we take a look at the sky. If you think about like taking a look at the Milky Way, like the objects that we could see, it's super small over there, but I was trying to say that we have the stars, the galaxies, and like other objects, quasars and other objects. But the main idea is that we try to understand these, at least in cosmology, trying to having a model, right? And right now we could stick with the lambda CDM model, right? Well, I prepare these mostly for undergrad students. And then, I mean, I'm not sure if everyone here knows, but like lambda CDM stands for like lambda, that usually describes the dark energy, and then CDM for cold dark matter. And well, we have this model that in some extent could be seen as a black box, right? We actually don't know what is going on, but if we try to understand, like, and try to model these, going deep into these studies, you can see that we have like many interesting sub models over there. And mostly what we do is trying to infer the cosmological parameters. Here I'm just like, have like two nice figures of like omega matter and sigma h. But we do way more than just like predicting these kind of parameters, right? So way more than trying to predict like the matter density or even like the clustering amplitude. And one of the main things that I would like to discuss today here is mostly related to the fact that we have traditional pipelines to do this cosmological inference. And this means that we have a model, right? Mostly speaking, for instance, here we have like the power spectrum. And the power spectrum is giving to us that more or less like the amount of matter that we have per scale, right? But we can have like many models varying these parameters, and we actually don't know which model describes better the universe, right? And then like the traditional pipeline goes there to actually like fit these models and with these parameters to fit our data and our unique universe, right? And in this scenario, it comes into account something really important in this traditional pipeline, which are the covariance matrices. And the covariance matrices, it's really hard to see here. This is like the usual covariance matrix, but you could see it like in the next slide, the normalized version of this. And these matrices are really important because they are going to describe like the error bars that we could have for these models. And well, how do we get there? Can we infer these cosmological parameters? Well, as I told you, we have only one universe, right? And then we should think about like having a model and having like the parameters theta for describing this model, right? Usually in the traditional pipeline, what we do is we model these using a likelihood, and in this likelihood is exactly what it comes like the covariance matrix, right? It comes right here. And this is measuring the difference between our data and our model, right? So if you think about the covariance matrix in this pipeline, which means like the sample covariance matrix for the power spectrum, for example, we have like, we're gonna measure like the correlation between the different powers of K. And these covariance matrices are as better as we increase the number of data that we have here, right? And there's another way to maybe take a look at this pipeline or at these matrices. That could be just taking a look at these images. So here, like you can see something like more than before because I'm presenting like the normalized version of these covariance matrices. And then you can see that there are some, okay, it's a bit hard to see because like it isn't so like right. But we could see that for some case, like in the y and x-axis, we have like the k, like the scales, right? But for some case, we have like a huge correlation that we can see like this shape over there, like this square block, okay? And we can see the other correlations in other parts of this universe. Usually this happens because you have like observation effects, for instance, masks in the sky, right? And then we are like generating these correlations. But what we could see and what is really interesting is that, well, the covariance matrices are nothing more than images, right? And then if you think about the one on the left and the other on the right, this means that if they are images, you could say that this one and that one are different just because of noise, right? And one could come here and say that, okay, this one is the covariance matrix generated with like really low amount of spectra. On the other hand, the other one, which is like super smooth, is generated with lots of spectra. So when we started thinking about this problem, I just thought, okay, if we could see the covariance matrices as images, could we apply maybe computer vision like techniques to try to just starting from the cheapest one, get like the expensive one? And this is exactly what I try to do, like in this kind of like problem in this scenario, which could be like from this matrices on the left, right, that I would call as bad matrices, get the image, like the images are the matrices on the right. And to do that, I will use not like another model, which could be a black box, but now let's use image denoising techniques, computer vision techniques to go from the left to the right. And well, I'm not sure how familiarized you are with these kind of techniques, but the main idea of using these image denoising techniques would be, okay, we have an image which is like really, really nice, right? These are like, if you are in this field of like machine learning and data science, you could see this data set a lot. These are like the handwritten digits, right? And then like over there, I have like this digit number 2, like with lots of noise. On the middle, we have the target image. And most of the time, what these image denoisers are doing is actually recognizing what the signal in the image here, like in this noise image, and removing like the noise and recovering what was like the signal instead of like the noise. So one of the ways to do that could be using autoencoders. Of course, right now have like most like way more advanced techniques to do this if you have already heard about diffusion models or so on and so forth. But the main idea is that we have convolutional layers which are specialized in dealing with images, right? And then we are gonna set up this as an autoencoder, which means that we have two parts, an encoder and a decoder part. And we have the images enter in this architecture the way that the image was like this square in the beginning. We're going to compress this image. It goes to a representation should be a latent vector, and then we are going to recompose to like recover the information from this latent vector to the image again. And through this process, we are going to remove the noise from this kind of like matrix to get the one which should be the cleanest version. Well, once again, just a bit about like these convolutional neural networks. For this kind of architectures, what we have are actually like some two really important pieces. And these two important pieces are, for instance, the kernels and the number of the filters. And I think that with this image, things are going to be like more explicit. So over here, once again, the handwritten digit number 4. And what is important is that we have these kernels, which are the small squares that we can have. And you're going to pass this through the image to extract information. Pretty much this. But for each kernel, we have a sequence of what we call as like filters that are going to be super important to extract each different part of information from the image. For instance, we could extract information related to the red band, so the red color of the image, or other properties too. And what to do here is actually like doing the convolutional operation, which is nothing more, nothing less than a multiplication between two matrices. And we are gonna like select information from these kernels, right, to each part. We're gonna output these into something that contains information related to the number of filters, and this ended up into like another cube of information, which is like actually compacting in a different way the same information that we had at the beginning. And well, it's really important when you're trying to do something new in physics, try to convince senior people that you are doing something which is not like super crazy. And when you try to do that, you should actually try to get close to the traditional like cosmologies, for instance. And one of the ways of doing this is actually trying to translate what I'm doing with machine learning to something that they could understand, right? So let's go back to something really traditional. For instance, this Wishart distribution. The Wishart distribution is a distribution that gives us new covariance matrices. Okay, why should this be important? Because this is a distribution that correlates the number of spectra that enters in the covariance matrices. And then, if we increase the number of spectra, we're going to have new samples from this distribution, which are better covariance matrices. And with this, we could actually sample more covariance matrices and see if our methodology was actually giving something similar to what people understand through these Wishart distributions. So what we did was like getting lots of spectra, right, and have a matrix that we call as the matrix with the maximum number of spectra, n max over there. Okay, with this matrix, we give this to this Wishart distribution, and then we measure the difference between the matrices that we're able to recover from the Wishart distribution with this best matrix as ever. Okay, this gives to us the mean square error is a difference between one matrix to the other that decreases as we increase the number of spectra. Perfect. Okay, but what I would like to say with this, because if we take the bad matrices and then we think about the same like difference, the same MSE through these matrices that should be the best one or not, we can have the bad matrices over there with the circles. But what's happening with the matrices that came out from my code, right? Well, these matrices came from machine learning methods developed to, for instance, go from a matrix with only 50 spectrum, that should be here, to something that, according to the Wishart distribution, should have something almost close by to 1000 spectra. Okay, so we're proving with something that many people know and already approve, right? The Wishart distribution, that the black box of the image denoising that we're putting there is actually increasing the number of spectra of this matrix. And then we are proving to traditional cosmologists that we have something that is acting the same way, right? So even though it's a black box, we can kind of like understand how does that work, and then understand what is going on with the output. The other thing which is really important when you try to put machine learning methods in these kind of problems is to obtain a machine learning model which is robust. And what does that mean? That means that if you have a robust model and you have a data set that the model was trained on, it's going to work if the model works, actually, right? So sanity check. Although the method is robust, if we change to another data set, and then we still get good predictions. So we trained everything on covariance matrices that came from really cheap methods. If you are from the cosmology research, you are going to see like EasyMox or any other fast and approximated methods. We just picked X halos, okay? And then we trained all the machine learning part on these spectra, on these matrices. Okay, but does that work in matrices that came from real any-body simulations, right? So that came from simulations that actually solve all the set of equations, which are super complex and blah, 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 and are not like approximations. Well, let's see. And at the end of the day, we are actually able to show that we could recover the parameters in both scenarios. So the model were actually like really, really robust. And it was pretty important to see that we put this working, starting from matrices with only 50 spectra. And we ended up in something, share this denoised in green over here, that remembers the kind of predictions even with this maximum number of spectra and mass, okay? So, and this was working on exhales, or what we call as like central cancer, because it was a really cute name, because that we figure out using Quixote. But this is a story for another another talk. Well, the point is that we are able to prove this, and well, the method was robust. We are borrowing a computer vision technique, and we are recovering like things from H naught, megabarons, and all the cosmological parameters that were available for us in these simulations. And we put machine learning in the traditional pipeline, right? Okay, but there are other problems that one could think about like traditional pipelines in cosmology. That could be, okay, sometimes we try to extract like these cosmological parameters using, for instance, the power spectrum, the one that I told you at the beginning, right? But there are like small caveats and problems in this, in trying to extract information using the power spectrum, because the power spectrum is very good to actually describe Gaussian distributions. But then we don't have like really good predictions or really good amount of information coming from what we call as the like from the Gaussian scale, like from the small scales over there. So there is no information that could actually trust from the power spectrum, but then we are retaining information from the larger scales, right? But then we could just came here and think about, okay, would be another way of doing that if we just use the galaxy catalogs, the raw galaxy catalogs information. And we came out with this idea, which was maybe really challenging, and that was like stressing like the community, because this is completely different from what like the traditional way of extracting cosmological parameters are. And we just converted like these galaxies with all their information into graphs, right? And graphs are really nice things because everything can be converted to a graph. I can convert you guys into a graph if you just like think about it in a really like specific way. But they're very good because at least by this image, you can see that they are a natural representation of the cosmic web. The shape is more or less the same, right? So we are tracing the cosmic web. And then we are going to put these graphs into this new machine learning pipeline that should be the graph neural networks, which are pretty good to deal with regular data. And then we are going to be able to extract the cosmological parameters. Okay, and while doing all this translation, like this method is really fast, and we don't have to impose any cut and scale. So different from the Gaussian problem with the power spectrum, we don't have to throw away any information. So for those of you who don't know actually what graphs are mathematical units that are really nice because like their main components are like described here. So we have the nodes, we have the edges, and then we have also like the graph by itself. The nodes can contain arrays that contain the node attributes, right? We could put everything there. The edges are not only connecting like the different nodes, but they can actually carry information, carry like another array with information. And then the graph by itself can have these global properties that actually describes the whole structure. So they are represented by these three numbers, or three set of arrays. And then in this problem, we are trying to do cosmology. So we are trying to actually convert like having the nodes as the galaxies and the node attributes as the galaxy properties. We thought about using the z component of their velocities, for instance. And forgetting the edges, we just like put these galaxies into a box, right? So we have access to their positions. And then we are connecting galaxies which are close to each other according to something that we call as R link. So the linking radius, that we say, oh, the linking radius is like 2 megaparsecs. And then we're going to connect all the galaxies which are inside this sphere. And then we have the edges. More than that, we have the edge arrays, which are like just like defined to take into account translation and rotational symmetries. And then we could think about like having the global properties, and we thought about using the number of galaxies. So at the end of the day, we convert the whole catalog into a graph that can be seen in that way. But the magic goes on when you try to see what is going on like behind the DNA, right? And the magic happens because of like this message passing scheme, which is supposed to actually take the initial graph and change only the values of the nodes and edge attributes, right? And then we have a new version of the graph, which contains the same structure, but has all these entities updated. So mathematically, we could go into the details. What is going on is actually like using the traditional neural networks, right? That we call as NLPs. But we are using them to actually update the information related to each edge. So we have the edge models, okay? And then the MLP is there, of course, but we have the update for the new edges in the different layers using the values for the previous nodes and for the previous or current edge, right? We have the node model where, once again, we put this information into array, which is going to be a simple multilayer per second, but then we are taking into account the values of the nodes, the values of the global property, and then the values of the edges. Over there, we have something that we call as multipooling operation, where we are going to take into account not only like the information to these galaxies, right, but to all the galaxies which are nearby. And this means that we could do like any compression of information that we want, but these are the ones that we chose, like taking into account the maximum value, the sum of the values, and the average over the edges. And turns out that this is like the main idea of what we are doing. We have a galaxy input, we convert this into a graph, we pass this through a message passing scheme that is gonna update the values, and then we compress the whole information of these galaxy catalogs into another array, pass this through another multilayer per second, and get the values for omega matter. Here we are using something that we call as in this case, the moment neural networks, and we are getting actually not the posterior distribution, not like the probability distribution, but two numbers, the mean and the standard deviation for omega matter for each galaxy. And we do this just modifying the loss function. It's more simple than it looks. But once again, we have to think about something that is robust. And it's important to let you know that for these things, for these galaxy catalogs, here we are dealing with simulations. And then can be really different from each other. I will let you know more details about it in the next slides. But this means that, okay, sanity check. If the method is working, we have like good predictions for omega matter for the same data set. But if we change the data set, this means that we don't get good predictions if the model is not robust. Although, if the model is robust, we actually have something that works no matter the data set that we have there. But why I'm here saying that I would like to have a robust model? Well, have you ever heard that we have like more than one hydrodynamical simulation to describe the universe? We have like Lucidity, we have like Wushu simulations, have thousands of simulations. So we don't know which flavor of simulation better describes the universe, right? And then we'd like to build that bridge, right? Between the real data, our unique universe, and then these simulations. And this bridge is not easy to actually build, right? Well, the first step of trying to to put these ideas into something that could work should be thinking about the hydrodynamical simulations. So, like the simulations that I told you at the beginning, the X-halos and the hot simulations, they only have like dark matter, right? Now we are gonna put gas information, so we have halos and galaxies. This means that we're gonna solve like more than the same set of equations than before because we put gas. There are like different formulations for these, Lagrangian formulations, Eulerian formulations. But what matters here is that there is a limit that we call as the resolution of the simulations. And in this limit, we have to came out with ideas that describe these scales in a different way. And this came up the idea that we have something that we call a subgrid physics, right? So different hydrodynamical simulations will have a different way to treat these scales, from star clusters to separation of binary stars and so on and so forth. And that's where the difference relies. So we have more than one simulation, we should have more than one way to try to understand the universe. Could be the machine learning able to overcome this difference? So we trained everything into this really nice set of simulations that we call as camels. And they are really, really nice because first, they are done to do cosmology, to do machine learning, right? Because for the first time, we have access to supercomputers and lots of like hours in these supercomputers to run many of these boxes with only 25 megaparsecs per each, but very many interesting things. So we have access to very cosmological parameters such as omega matter sigma wave. That's why I put them into the beginning of the presentation as cute characters. And then we have access to modify other things such as two parameters related to supernovae. And in these simulations, we call them we vary two of them related to supernovae feedback and two of them related to AGN feedback. And well, over there, many of the difference actually play the game of these hydrodynamical simulations. But because we have access to this computational power, we can vary these parameters, and then we are gonna vary them into something that if you go deep into more details behind the simulations, we have what we call as LH set, where we are varying all the six parameters, right? Varying actually the different journal seeds, and then we're training and testing the machinery using this difference, right? So we have access to these 6 different subgrid physics schemes, right? So these 6 different hydrodynamical simulations. So Astrid, Illustrative, Magneticon, Simba, SP28, and Sequigo. And over all these different groups of extreme amazing people trying to develop their own hydrodynamical simulations, we have this difference, right, going on. It's important to let you know that SB28 is illustrative, but very more than the 6 parameters. And in the case of Swift Eagle, over here, we're taking into account one simulation that uses a different way to find the substructures, which are substructures in the tables, right? That we call as illustrator. In all the others, we are using subfine. Details that we could explain later or in another presentation, or if you want to discuss later too. The point is that if you just take into account an image, again, of the simulations, and then over here, I would like to actually, I was supposed to actually bring the video, but over here you can see just a snapshot, so just a picture of these different simulations evolving through time through redshift, and then here is just for redshift 0.09, right? And although all the simulations are supposed to describe the same universe, they are different, just by that, right? So you have blue and red representing the temperature and the density of gas, right? And then in Simba, we have way more regions which are way more warmer than massive and so on and so forth, right? So even though they describe the same universe, just by eye they're different. So it's really, really hard to actually come out with machine learning methods that could actually overcome this difference. But what we did was actually thinking about the main properties that could be similar in all the simulations. And of course, not thinking about the similar properties, but thinking about the best machine learning translation to this problem, right? So using only Astrid, right, simulations, we trained the GNN over these galaxies using only their 3D positions and the Z component of their velocity. And we are able to get the first machine learning method, which was robust enough to overcome the difference over all these simulations. So over here, you can see the famous plots in cosmology, or in machine learning or data science, which represents the truth minus inference. And then on the y-axis, we have the truth. So we could see that we are always close by 0, right? And it doesn't matter how the difference between these different simulations. But as I told you at the beginning, we have to actually convince people that we are doing something close to the traditional methods, right? So instead of coming out here with a wish-hard distribution, what we did was actually translating each part of the GNN into an equation, right? To convince people that we are dealing with physical information, okay? So in order to do that, we use a symbolic regression. And then we have an equation to describe the edge model, the node model, and then the final MLP. And for those who are not used with this symbolic regression, what we do is actually select our input variables, initialize the scheme of looking for equations that are going to have to contain operations such as addition, subtraction, just multiplication, so on and so forth. Just pick which ones you prefer to use. You are gonna then come out with equations that are gonna be selected and muted through like one simple equation that you have at the beginning. And you're gonna see, okay, is this complex enough? Am I going to stop and then try again? Or can I just jump into the result and this could be the best equation methods? So this is more or less the main idea of like how we do this with symbolic regression. And with this, we had a really nice set of equations for these GNNs. Okay, we have equations, they are there. They're simple. Unfortunately, they're not so simple, but they actually contain everything that we physically care about, right? So over there in the edge models, we have access to gamma and beta, which are nothing more, nothing less than taking account of like these populations, right? So it's the distance between the different galaxies divided by the Deepen radius, so on and so forth. Beta is actually an angle for us. So we are taking into account information related to shape and filament or structure. And with that, we got a model which was robust not only over the hydrodynamical simulations, but over the different dark matter simulations too. So, taking into account observation effects, we try to think if this methodology could work with maybe errors that we see in observations. But we don't have simulations, so we have to mimic these errors, these observation effects, into the simulations. So we talk about having mask effects. So if you take a look at images from surveys, you can see that sometimes we just figure out something that we call as a bright star. And the bright star is actually like messing up all the information from the galaxies which are nearby them. So in these real surveys, they just like messed out these bright stars, and then we could have access to the information for the galaxies which are around. So we have to take these kind of mask effects into account. Sometimes you only measure red galaxies or blue galaxies, and because they have like a lot of properties, saying that some are older, some are like younger, they actually are like in different configurations of space too. And then sometimes we have to take into account errors in the velocities, right? Because I told you that we're only using position and velocities. So we try to come out with ideas to put these observation effects into the simulations, and we retrained the model that we had before. And surprisingly, the model was robust enough to take into account masking effects, to take into account only blue galaxies, which are actually clustering in a different way than like red galaxies. We took into account different like perturbations in the velocities, and even though the model was still robust. So should have something which we could actually use in real data. Well, if you go to this analysis in cosmology, we know that we have these approximated methods, and they are way faster to run than these hydrodynamical simulations that contains like the whole complete set of equations and solutions and blah, blah, blah. So we started asking ourselves, okay, does that would work if we take an approximated method for the hydrodynamical simulations, and then we picked what we call as semi-analytical models, or SEMs, okay? And we try to see if that was working on that. To just let you know, for the semi-analytical models, we're not solving all the set of equations. We're trying to actually like having analytic prescriptions to track these dark matter objects evolving through time. And with this idea, which is really, really amazing, we could actually like have a comparison from these hydrodynamical simulations. If you think about like the evolution of these like subhalos evolving through time to a halo, and here's more or less like the idea of what how a merger tree actually works on these semi-analytical models. I could go actually in way more details about them, but the main idea is to actually say that even considering these really amazing, like, but still approximated solutions, the method is working. So to actually have these things working, we have to figure out a data set which is wider enough, right? So in here, what we did was actually putting this to actually like having this wider model for this sun, which is actually L galaxies. We trained the machinery again, and the model was robust over different semi-analytical models. So it was selectively working on L galaxies, but it was also working in other SEMs. For instance, Gaia, Astrid Sun, Sharp, and that was amazing. But it could be even better if you could extrapolate the predictions for the hydrodynamical simulations. And yeah, we could actually like show that. for all the same set of simulations that we have at the beginning. So yeah, we could actually put this pipeline to work, even thinking about these methods. But there's just a last thing that I would like to show you for you today, which is actually a really nice idea, which is like, okay, I told you that we could extract cosmology from clustering, right? So from the power spectrum, and then maybe using these galaxies, like all the galaxies that we have access to. But there is a really, really crazy and beautiful idea of trying to get cosmology from single galaxies. So we are not taking into account any clustering around, right? If you only think about these simulations and think about maybe using their stellar mass, maybe the black hole mass, maybe the star formation rate, only single galaxy properties, could we extract the mega matter? Well, of course, this idea started with Paco and like trying to do this from single galaxies, not for symbolic regression, but I was really happy to actually collaborate in this work, which was actually related to the fact that we are trying to extract these, but with equations. So once again, symbolic regressions, right? Okay, so we have all that ingredients, all that variables, and we put like the machine learning symbolic regression actually came out with an equation. But it's not like only the matter of coming out with equation that physically makes sense, right? Like that is like containing the physical variables, but it has to actually make sense physically, right? So of course, Quito had a lot of work thinking about maybe the best set of like combinations for these variables, and which means that this is the equation. It's not simple, of course, but it actually is like using all the components for one single galaxy. So using like the stellar mass, what we call as like this combination of stellar mass and gas mass. We have like this S score, which is gonna to correlate like the effective volume, right? Using like the effect velocity, sorry. And then like the compactness rate ratio and everything else. But coming out with this idea, we have to think about the physical interpretation about the different terms. The first one could be translated into the mass and least relation. The second one is gonna represent the mass that is enclosed by a universe expanding with H naught. And the last one could be related to the amount of baryons, right, that we have in account for this single galaxy. And this could actually measure like the feedback effects that we have like in the game of these hydrodynamical simulations. And with this equation, and it's important to let you know that we have to actually like could be in some extent like a linear equation in terms of like these C0 and then this A naught, right? Which has like this sin on top, which are just numbers that we have to change to tweak a bit for getting the predictions from one simulation to another. But with only one equation and putting the machine learning to actually like translate this, we could extract omega matter. And we are able to actually show that, yes, indeed, we can extract omega matter and we have something which is robust, apart from this tweak for these parameters, that can predict omega matter through all the simulations too, and just from one galaxy. So this is really, really amazing. And I think that to end this talk here, I would like to just like conclude saying that, okay, if you're really crazy, don't matter, if you have an idea and would like to put this in practice, you have to just find out a person which is like excited to do this with you. So I started this like trying to put machine learning for trying to solve problems in cosmology with these denoising cosmological covariance matrices. And we are able to put these machine learning methods to work in traditional pipelines. So we are improving traditional pipelines with this project. It's really amazing to see that if you think about extracting information from galaxies, set of galaxies, not doing traditional power spectrum, right? And not like traditional MCMC and so on and so forth, but translating these to graphs and GNNs, we have something which we only need positions and velocities, right? The model is robust to observation effects. The model is robust to like approximated methods, right? And we might have been like giving the first steps to real data, like before applying these techniques to real data. And yes, we don't have to restrict ourselves to try to do only like the traditional things, because even though for this simulation-based inference with graphs, we have like the galaxies, their positions, it's more or less the same way that we measure power spectrum, right? Of course, after the translation. But we can go even crazy and try to get cosmological information or any information, maybe with just one galaxy. And I think that's it, guys. I hope I could give you like some exciting about like trying to use machine learning to do cosmology. And that's it. Let's try to infer the cosmological parameters with galaxies. Thank you.
So much. Do you have some time for questions? Are there any questions from the audience? I have one question. Okay, so you said that you don't lose any information, or at least none of the information that you care about from putting it into this graph format. What is it about making it into a graph that is so nice for neural networks to handle? Or I guess what advantage does that have over representing it in some different way, I guess?
Well, it's actually, this is a really important and interesting question. And I would say that.
Repeat the question.
Oh, yes.
Oh, yeah.
Yeah. So hi guys. So the question is more or less related to the fact that, okay, the first part of the question is like, it's really important to see that we don't lose any kind of information, right? Like we don't have to cut scales when we go to this translation to galaxy catalogs, to graphs, right? And I think that he is asking about the fact, like, is like the idea of like these being a really good methodology just because we are doing this translation to graphs, or because like the whole like translation with the GNNs too? Well, I think that first, we are actually like doing this translation between the galaxy catalogs to graphs, right? So we are not like saying, oh, we are gonna to just like throw out these galaxies or throw out these scales, because we are actually like putting all the galaxies in the catalog there, right? The other thing that we're doing this translation is actually like connecting galaxies which are close to each other, right? So in this translation, this construction is really important. So because of that translation, all the information should be there, okay? Although if you just have like your galaxy catalog translated into a graph, you will never be able to come out with like the cosmological parameters without thinking about tweaking a network to actually like came out with the answer of a megamatter, to doing with this simple regression task, right? So like both are important, the translation to graphs and then the architecture of the GNN by itself. But yeah, some people could say that because we are connecting only galaxies which are like close by each other, we have like some constraint on scales. But as more GNN passage GNN layers we have, more this information is going to propagate from one galaxy, which is here, and connect with these galaxies, to the galaxies which is here, and then the third galaxy here, and so on and so forth, right? So to some extent, all the information is still there. And like different from what we do in the traditional pipeline, we don't have to say, oh, we're going to constrain, like to just trust on the power spectrum up to this scale, throw out this other information, and then we're going to match our theory with the model only for these scales. So yeah, it's a mix of everything.
With the translating the galaxies into, or the clusters into a graph, we'll went to like choosing linking radius.
Yeah, so the clusters are there, but like according to the size of the linking radius, we're gonna to like in some extent propagate the information to more galaxies which are nearby. So if you think about like, okay, what should be like the cluster scale that you think about? It should be more or less related to like the linking radius that you have. I'm not sure if I answered your question.
Correct me if I'm wrong, was the question, how do you choose the linking radius?
Oh, how do I
Yeah.
choose? Oh yeah, it's important. Sorry about that. So the linking radius is another, for this scenario, in the way that we deal with this problem, it's another hyperparameter of the whole content of like the neural network and so on and so forth. So we start like from really, really small linking radius, and then we go to something that does not connect all the galaxies in the catalog, because then things are gonna be super, super complicated, right? Then the network scales to another level too. So yeah, in some extent, we are constraining up to certain scales too. Yeah, but the linking radius is like actually chosen by this set of hyperparameters. The way that we actually do that is looking for these hyperparameters using Optuna. So we are using like a method that's called TP sample, and then we're gonna actually like try to see the best combination of them to give the best like the lowest loss function for the validation stage. Yeah.
Is machine learning becoming standard in your field? Like something that a tool that or a set of tools that people are using more and more?
Yeah, machine learning is right now like used more and more, but I would not say that is like something that people are gonna like just give up of like the traditional methods to do machine learning. It's just like an alternative method, as well as we have like many like we have EFT, we have like this solutions and everything else. Like you have like many different scenarios for doing cosmology. So I think that we are not in the pace or in the level that we're gonna give up from the traditional methods to do machine learning. Nope. And especially because even though we try to figure out what is going on behind, like the black box of the machine learning, not everyone actually trusts on what you're doing, even though we can understand what is going on behind the network and everything else. And I think that one of the reasons why people don't trust that we can actually put this in practice for your data is because, yes, I told you at the beginning that we have lots of data, right? Although, if we go to try to mimic what we have on clusters, even though for like clusters that we have right now, we have like approximated methods which are actually like mimicking our galaxies, right? Our observations. And to actually put machine learning in there, we should be able to actually like having these small boxes as camels to actually mimicking the whole universe. So we should rerun these for the different surveys and so on and so forth, which is like just scales the complexity of what we have to run. So yeah, in some extent, it's really good. We have access to this, but to put this to actually like mimic real observations, we have to figure out if something. And one way should be maybe using only one galaxy, one single galaxy, instead of like having to have these like many simulations to have because over here we are marginalizing over the values of omega matter. As I told you, we have like variations of omega matter from 0.1 to 0.5, and in some extent we believe that we are around 0.3 in the fiducial cosmology. Our universe relies there. So imagine to have like many of these realizations for like these hydrodynamic simulations to service. Yeah, so we are trying to get there and like with an alternative method. It's not like something that could rule like the world. But yeah, I'm really excited, even though.
That at a time. But if there are any other questions, feel free to chat with the speaker afterwards. So thank you all again so much for coming to this week's Compass lecture. If you haven't already, please remember to sign in on your way out. It really helps us out a lot to keep the lectures going. And let's thank our speaker one last time.
Yes.